the video. Okay, so let's start now. Okay, so in the next two lectures, so we are going to talk about chapter 5, so property of a random sample. Okay, so as an introduction, so let's go to this page, this lecture note, so which is the one we talk about at the beginning of our course, okay, about the whole logic of this cause sequence statistical inference. Okay, so in all previous 4 chapters, so actually we are talking about the distribution of the population. Okay, so basically the goal of statistical inference is so we want to make some decisions and predictions about the property of a population that we want to study. Okay, so in chapter 1 to 4, so basically we are talking about the those probability distributions, for example the normal distribution or the gamma distribution, etc. So those are all about the distributional assumption of this population. Okay, so now for example, if we assume that this population has a normal distribution, so with the 2 parameters, the mean and the variance, so those are the parameters about this population. So now our goal in this chapter, so basically in real world, so those population parameters mu and sigma, so we don't know. So now we need to draw a random sample, okay, like in this here, we draw it here. So which is a small portion of the population. Okay, so we write this as x1, x2 up to xn. So we have a size of n individuals of this sample. Okay, so now our goal is we try to calculate some quantities. So actually they are called statistics. So those statistics based on this sample. Okay, for example, the sample mean x bar or the sample variance s squared. Okay, so we try to calculate those quantities based on this random sample. Okay, and then based on those quantities from this random sample x bar, s squared, etc. So we use those quantities to make inference about those population parameters. Okay, so this is the process we call it statistical inference. Okay, so basically the goal of chapter 5, so this chapter, so we are going to study the property of this random sample and also the properties of some statistics based on this random sample. So for example, specifically for x bar and s squared, the sample mean and sample variance. Okay, and then in next semester, okay, so basically chapter 6 to chapter 9 of this textbook, so you're going to study the technique and methods for this inference. So that is how to use this sample statistic to make inference about the population parameters. Okay, so this is the logic here about this course. Okay, so now let's turn to our lecture note of chapter 5. Okay, properties of a random sample. Okay, so first let's start with the definition of a random sample. Okay, so you can all hear me, right?
Yes.
Okay, so let's continue. Okay, so as I mentioned, so we need to draw a small portion of individuals from this population, so which forms a sample, and then use this sample to make inference about the population. Okay, so then what is the definition of a random sample? Okay, so this number of n random variables x1 to xn are called a random sample of size n. So total number of random variables is n. Okay, So this is called a random sample of size n from the population fx. So fx is the distribution we assumed for the population. So for example, the normal distribution, gamma distribution, etc. Okay, so this is called a random sample if those x1 to xn are mutually independent random variables. And the marginal PDF or PMF of each xi is the same function fx. Okay, so basically here we are talking about two properties of a random sample. So first, each random variable in this random sample, so they are mutually independent. And we talk about the definition of mutually independent in chapter 4. Okay, so that is the first property. Okay, second is, so each of those xi have the same marginal distribution. They have the same PDF or PMF. Okay, and then this PDF or PMF is the same as the population distribution. Okay, so that is the distribution we assumed for the studied population. Okay, say for example, if the population follows a normal distribution, so then each of those xi, so in this sample, so they are mutually independent, and they also follows the same normal distribution of the population. Okay, so therefore there is an alternative name for this random sample. So they are called independent, identically distributed random variables. So IID random variables with the PDF or PMF fx. Okay, so this is the definition of a random sample. Okay, so let's compare this with the definition of sample. So we saw at the beginning. Okay, so the definition of a sample is more general. Okay, so basically a sample is just a small portion of the population. So we draw to study the property of this population. Okay, sometimes this sample, the individuals we draw in this sample can be dependent on each other. Okay, but here we are talking about the simplest and ideal case. But this case is very common, so which is the random sample. So in other words, here we assume those individual observations in this sample are independent and identically distributed. So IID. Okay. So, and we will talk about this, throughout the whole, throughout all the rest chapters in this textbook. Okay. So in other words, we are talking about the, the way of making inference based on IID random sample. Okay, so we assume those observations in this sample are IID. Okay, so this is the assumption for all the rest of all the rest chapters of this textbook. Okay, so okay, so now let's look at what is the result about the joint distribution of this random sample. Okay, so because those x1 to xn, so they are independent and identically distributed. Okay, so based on what we learned in chapter 4 for independent random variables, so then we will have this result for the joint PDF or PMF of the random sample x1 to xn. So which is given by the joint PDF or PMF, so is given by the product of individual PDF or PMF of xi's. Okay. And then this fxi is the same as the distribution. So meaning the PDF or PMF of the population, right? Okay. So that is this is just the direct result based on the independence of those random variables. Okay, so then the joint PDF of PMF can be written as this product. Okay, and if the PDF or PMF of this population distribution is a parametric family, okay, so that is what we learned through the whole semester. Okay, so we assume, for example, like the normal distribution, gamma distribution. So those distributions are determined by those parameters like mu, sigma square. Okay, so then we call this parametric distribution, meaning those distributions are determined by those parameters. Okay, so if this is the case, so means the population distribution fx is a member of a parametric family. Okay, so then we will use this symbol theta to denote the population parameters. So for example, the mu and sigma square in normal distribution. So we use theta to denote them. Okay, so we will write this joint distribution of this random sample x1 to xn, so that those are depend on the parameter theta. Okay, so further can be written as this product. Okay, product of each individual distributions of x1 to xn. Okay, they are also depending on the parameter theta. Okay, so this is the definition of random sample and their joint PDF or PMF. Now we can write in this way. Okay, so now let's see one example about the exponential distribution. So here we assume the population distribution is an exponential distribution. Okay, and then we have a random sample x1 to xn. So they are IID random sample drawn from this population with exponential distribution. Okay, so now how can we write the joint PDF of x1 to xn? Okay, so based on what we just discussed, so that is the product of each individual PDF of x1 to xn, so which is an exponential distribution. So this is the form of exponential distribution. Okay, and then after some rearrangements of term, okay, so we have this. Okay, so this is the joint PDF of the random sample from the exponential distribution. Okay, and support of this, so of course each xi should be greater than 0. Okay, so any questions here? I think it's straightforward, right? Okay, so now let's look at the, based on this joint PDF. Okay, so now let's look at some probability, the joint probability of x1 to xn. Okay, so here for example, if we want to calculate this joint probability based on this random sample x1 to xn. Okay, so because x1 to xn are IID, so independent and identically distributed. So based on the independence, so as we learned in chapter 4, okay, so this joint probability, so we can write this as a product of each individual probability. Okay, and then for each of this individual probability, so that is this probability is 1 minus the CDF of exponential distribution, right? So the CDF of exponential distribution, so that is 1 minus EXP, that is EXP of this x divided by beta, right? So this is the CDF of exponential distribution. Okay, so this is, so then we have this. Okay, So if we just plug in the number, okay, to this form of CDF of exponential distribution, okay, and then we multiply them together, okay, so then we have this. Okay, so this is about the example, a simple example, to demonstrate the joint PDF of IID random variables or IID random sample. Okay. So here, basically, the IID random variable is the same as a random sample. So when we talk about this random sample, so we mean those observations or random variables we draw from the population. So they are IID. Okay, so any questions here? Okay, so now let's move to the next part. Okay, some notes about this IID random sample. Okay, so here we assume all the observations or random variables in this random sample are IID. Okay, so now let's consider if this is correct in practice. So compare this with the reality. Okay, so in practice, we have the following scenarios. So when we draw a random sample from a population. Okay, so first, so if we have an infinite population, so infinite population, the population can be considered very large, the size of the population. Okay, so usually in that case, we can easily get IID random samples. Okay, if the population is very large, almost infinite. Okay, so then we can say this individual draw from this population. So they are easy to meet the condition of IID, independent, and then identically distributed. Okay, so the second scenario is most of the case, so we will have a finite population. Okay, finite population. Okay, so then we will still have two scenarios. The first one is we do the sampling with replacement. Okay, so this we have briefly started this in chapter 3. So when we talk about the hypergeometric distribution. Okay, so if we do the sampling with replacement, so each time we draw the individual, draw the observation, and then put it back to the population. So then each individual will still have the same probability to be selected. Okay, so in this case, it is still easy to get IID random variables, right, for sampling with replacement. Okay, so second scenario is sampling without replacement. Okay, so in this case, those observations in the random sample, so they still have the same marginal distribution because they are drawn from the same population. Okay, but now they are not mutually independent. Okay, but when the size of the population, so capital N, is large, so they are still close to be independent. Okay, so basically here we are talking about, the justification of the IID assumption. Okay, so basically for infinite population, okay, we can easily meet this assumption of IID. Okay, and for finite population, sampling with replacement, we can still get IID random sample. Okay, the only exception is for sampling without replacement. So here, those xi's can be dependent. Okay, but when n is very large, so they are still close to be independent. Okay, so basically this means in practice, this IID assumption is still useful and feasible. Okay, so that is the meaning of the notes here. Okay, and here I have just one remark that is beyond our course. Okay, so basically our course are all about, so in the next few chapters, are all about the making inference based on IID random variable, so based on this random sample. Okay, so there is a specific field called sampling. Okay, sampling. This is a specific field in statistics. So this field is mainly talk about the, the methods and theory underlying this process, how to draw this sample, and how what is the property of this random of the sample. Okay, so in that field, sampling, so there are more complicated situations. So both in theory and in terms of theory and methods. Okay, so this is of course beyond our course. Okay, but it's good for you to know. So this field called sampling. Okay, so now let's back to our example of this IID assumption. Okay, so in this example, so I just want to demonstrate this point. So even if this population is finite, but when n is large, the size of this population is large, so then those x1 to xn are still close to be independent. Okay, so this example is like this. So here we have a total of 1,000 individuals forming a population. Okay, and now we want to draw a sample of size 10. Okay, sample size is 10. Okay, so we assume this 1,000 individuals, we number them with 1, 2, 3, okay, so on up to 1,000. Okay, so now let's look at the two calculations. So the first one is basically we want to calculate this probability. Okay, so that is we have all the 10 individuals in this sample. So they are greater than 200. We want to calculate this probability. Okay, so first one is the exact calculation. So without the IID assumption. So that is based on what we learned in chapter 3. So about the hypergeometric distribution. Okay, so if you remember that, so the hypergeometric distribution is to calculate the probability for finite population. Okay, so here we have 1,000 individuals, and we want to find this probability. So every observation in this sample is greater than 200. Okay, so then this probability is we need to draw all the 10 individual from the rest of 800 individuals, right? So that this we can divide this population by two parts. So the first part contains the 200 individuals with number less than 200, and the second part contains the 800 individuals with their numbers greater than 200. Okay, so we need to draw 10 individuals from the second part contains 800 individuals. Okay, and then we draw 0 individual from the first part. Okay, and then we divide it by the total number of ways to draw this 10 individual, right? So then this is the probability of this. Okay, so the exact calculation gives this number. Okay, and now let's look at what is the result that we assume each individual are independent. Okay, each of those 10 individuals in this random sample is independent. Okay, so then based on the independence assumption, we have this probability is this individual probability to the power of 10. Okay, so, and then this individual probability is 800 divided by 1000 to the power of 10. Okay, and the approximate result is this. Okay, so now from these two numbers, so we can see, so this n is relatively large, about 1000. So then this calculation based on the exact calculation, so meaning we assume those xi's are dependent. Okay, and compare this with approximate calculation. So they are quite similar. Okay, so this basically shows the this part. So if the population size is large, so then those xi's in the random sample are close to be dependent. Okay, so any questions here? Okay, so now let's move to the next part. So the next part is about the sums of random variables from a random sample. Okay, so although the name is from textbook, so that is the sum of random variables from random sample. But basically, in this part, we are talking about two things. Okay, so first one is the sample mean x bar. Okay, the average of the random variables in this random sample x bar. Okay, and second quantity is the sample variance, so which is defined here. Okay, so basically this part we are going to talk about the properties of x bar and s square. Okay, so let's move to the next page. So here, let's first talk about a definition called statistic. Okay, so we are all talking about statistics. So then what is the definition of a statistic? Okay, so here we have x1 to xn is a random sample of size n from a population. Okay, so now we let this t of x1 to xn be a real valued or vector valued function whose domain includes the sample space of x1 to xn. Okay, so then the random variable or random vector of y equals t is called a statistic. Okay, and the probability distribution of a statistic y, so it is called the sampling distribution of y. The sampling distribution of y. Okay, so basically, we can say a statistic is a function of a random sample. Okay, is a function of a random sample t of x1 to xn. Okay, and the distribution of a statistic y is called the sampling distribution of this statistic. Okay, so based on this definition, so as we mentioned, a statistic is a function of a random sample. So in other words, a function of x1 to xn. So it should not be a function of an unknown parameter. Okay, so that means, so those unknown parameters are, so now, for example, the normal distribution have the population parameter mu and sigma square. Okay, so based on what we talked about at the beginning, so now we don't know the true underlying population parameter mu and sigma, and we need to draw this random sample to make inference about mu and sigma square. Okay, so then this statistic is calculated based on the random sample we draw. Okay, so it should not contain unknown parameters of the population like mu or sigma square. Okay, so second note, so is what we already mentioned. So this statistic should be a quantity computed from the sample data, okay, based on the random sample x1 to xn. Okay, so because this statistic is a function of random sample, so meaning the n independent NIID random variable. Okay, so then itself is also a random variable or random vector. Okay, the statistic. Okay, so the last note is more about the notation. Okay, so a statistic is usually denoted by capital letters of the English. Okay, so and the population parameters, so like the mu and sigma square, so usually are denoted by Greek letters. Okay. Okay. So this is the definition of a statistic. Okay. So basically the idea is we draw this random sample. Okay. So now, and then we calculate some statistics. So for example, x bar and s square. And then we use those statistics computed from this random sample to make inference about the population parameters. So this is the logic of statistical inference. Okay, so in this part, next we are going to study the two important statistics. So that is the sample mean and the sample variance. Okay, so first, the definition of the sample mean. Okay, so that is, we all know, so basically that is the average of the n observations in this random sample. Okay, the next one, the sample variance. Okay, sample variance. So that is defined in this way. Okay, so here we have this n minus 1 in the denominator. Okay, for the sample variance. Okay, and then here the x bar is just the sample mean. So this is the definition of sample variance. Okay, so a related definition is the sample standard deviation. Sample standard deviation. So which is the square root, the positive square root of the sample variance. Okay, so we have sample mean, sample variance, and the sample standard deviation. So those are the three important statistics. Any questions? No? Okay. So now let's move to some results about the sample mean and the sample variance. Okay. So first we have this result. Okay. So here x1 and xn be any numbers. Okay. And then x bar is their average. Okay. So we have those two results, those two formulas. Okay. So first one, so the minimum number of A, the number A that minimizes this square, sum of square, is the sample average. Okay, so to prove this part, the first part here, okay, so here we can use the similar idea, so as we did in chapter 2. So where we have shown here we are talking about the sample average. Okay, in chapter 2, we are talking about the population average, right? So that is basically the expectation, the EX, that is for the population. Okay, so remember in chapter 2, we are talking about basically the expectation of X is the center of the population. Right, so then it has the smallest distance. So on average, this means the smallest distance. So which is the center of the population. So which is the expectation of X. Okay, so here the meaning of this is the average of the sample mean. So basically that is the average of all the observations in this sample. So which is the center of this sample, right? So on average, this is the small distance of all the observation to the center is the smallest one. Okay, so this is has the same meaning of the expectation of x. Okay, and to formally prove this, so we just need to do some algebra here. Okay, so here we add the x bar, add the x bar, and also subtract the x bar. Okay, and then now we just expand the square here. Okay, so basically we have three terms. Okay, so the first one is the square of xi minus x bar. Okay, and then the second term is x bar, the square of x bar minus a. Okay, and then we have the interaction term between these two terms. Okay, so and after some algebra, so you will see this interaction term is 0. Okay, and then we have this. Okay, and then the first term is so we want to find the value a to minimize this. Okay, so then we will just need to look at the second term contains a, right? So because we have a square here, so this second term is non-negative. So the smallest value of this second term is when a equals x bar. So the second term is 0. Okay, so then we have proved part A. Okay, so and this, we also have this part B. Part B, that is about this relationship of sample variance S square here. Okay, so the first part of this equation, so that is just the definition of S square. Okay, so if you look at definition, so that is defined in this way. Okay, so then we have the first part. Okay, so basically the second part is about gives us a formula to like an alternative formula to calculate S square. Okay, and then we also have this equals this. Okay, so that is the sum of xi square. So minus n. N is the number of observation, the sample size. Okay, multiply x bar square. Okay, and then how to show this? So this is also easy to see. Okay, so based on this, okay, so now we take a. We just take a as 0. Okay, take a as 0. So then this part becomes this x I from 1 to n, okay, and xi square. Okay, so this part when a is 0. Okay, and then this part we take a as 0. Okay, so then this part becomes x bar square. Okay, and then we have the n x bar square. Okay, so then this part becomes n multiply x bar square, right? N multiply x bar square. Okay, so then if we compare this with the formula we want to show, right? So then this has the this sum of xi minus x bar equals sum of xi square minus n multiply x bar square. Okay, so can you see this? This is just some algebra, so you will see this. Okay, so basically this one gives us an alternative formula to calculate S square. Okay, in addition to the definition, okay, here, in addition to the definition of S square, this is the definition formula for S square. Okay, so here is an alternative formula to calculate S square. Okay, so now let's move to the next part. That is some properties about the mean and variance. Okay, so here the xn, x1 to xn is a random sample from a population. Okay, so here is about some properties about the expectation of and variance of functions of this random sample. Okay, so here the gx is a function, okay, such that this expectation of g and variance of gx exists. Okay, so here because x1 and xn are IID, okay, so then we have this g, a function of them, so evaluate on any one of them, so that is g1, g2, okay, and the gn, so they are all the same. They are this function of g evaluate on each individual x1 to xn, so they are all IID. I should not use the equal sign here. I should say they are also IID. Okay. So because they are also those G1, GX1, GX2, and GXN, so they are also random variables. Okay. And then they are functions of IID random sample. So they are, those G functions are also IID. Okay, so meaning they are independent and identically distributed. Okay, so now we want to look at this. Okay, so that is the sum, the expectation of the sum of those GI, those functions from G1, GX1, GX2, and GXN, the sum of this. Okay, so the expectation of the sum of this is this one. Okay, so that is n multiply the expectation of gx1. Okay, but here the gx1 is also the same, is also identically distributed as gx2. Okay, so this is also equals to the expectation of gx2, right? Yeah, because here the gx1, gx2, they are IID. Okay, and then so on. So we can write this as n multiply expectation of gx3. Okay, and so on. So because all gx1, gx2, and gxn are IID. Okay, so and also this formula, second formula, gives us the property of the variance of the sum of gxi. Okay, variance of the sum of gxi. So which is this? So n multiply the variance of the individual variance, n multiply the variance of the individual one. Okay, so of course this is also the same as the variance of g x2. Okay, the same as the variance of g xn. Okay. Okay, so now let's see how to show this, how to show those two formulas, those two properties. Okay, so first one is easy. So this is just by the property of expectation. Okay, the property of the expectation. So that is what we have learned before. So this expectation, so we can directly evaluate this expectation for each individual, because this is a sum. Okay, so we can take the expectation for each individual gxi and then sum them together, right? So this is the property. We have this linear property of the expectation. Okay, so and then as I mentioned, so each of those gx1, gx2, and gxn, so they are IID, so they are identically and independent distributed. So then their expectation is the same. All equals expectation of g x1. Or you can write this as expectation of g x2, and then so on, right? So then the sum of n terms will become this n multiply expectation of g x1. Okay, so this is the first formula. Okay, So the second formula, so the variance part. Okay, so this one we need to first write out the definition of the variance. Okay, so definition of variance is the expectation of this square term, right? So that is this. So remember the variance of x. So that is the expectation of this x minus e x square. Right, so this is definition of variance. So now we just write this as a variance, by the definition of variance. Okay. Now let's see this. So, okay. So here this expectation. So we have already in the first formula. We have shown this in the first formula. Okay, so the expectation of sum of this, so will equals the n multiplied the expectation on each individual function, right? Okay, so then we will write this. We have n multiply expectation of g xi. Right, so this expectation is n multiplied the expectation of g xi. Okay, so you can write this as g x1, x2, or any one of them. Okay, or just the xi. So because each expectation of g xi, they are the same. They are IID. So the expectation of them is the same. Okay, so now we will rearrange this to give each individual xi to merge with the first term. Okay, to merge this, basically it contains n expectations, right? And then we gave each individual expectation to the first term, right? So then we will have this, we can write this as a sum of this expectation of each individual gxi. Okay, so now we need to expand this square term. So we want to expand this square term. So this is the square of a sum of those n terms. Okay, so in total there are n square terms. Okay, so first there are n terms of this. Okay, so basically we need to expand this square. So first we will have those square terms, right? So it's like this. So we have the sum. Let's write this. So I will write this a1 plus a2 plus an. So basically we are expanding this square of sum. Okay, and then each ai here is the g xi minus the expectation of g xi, right? So that is each ai. Okay, so to expand this, so first we will have n squared term. Okay, so you know what I'm talking about, right? Okay, so we need to expand this. So first we will have the sum of ai square. So there are n terms of those square terms. Okay, and then plus this interaction term of ai aj. So like this. Okay, so let's first look at those first n squared terms, in terms of this. Okay, so then we have this. Now we also have an expectation, right, in front of this square. So we have an expectation of this square term. Okay, so then this is just the definition of the variance of gxi. The variance of gxi. Okay, so here, because as I mentioned, each of those gxi are IID. Okay, so then we can just write this variance as a gx1 or like gx2, so that they are all the same. Variance of gx1, variance of gx2, so they are the same. Okay, so now let's look at the remaining, this interaction term. So n multiplied n minus 1, those interaction terms of this form. Okay, so then the expectation of this interaction term. So if you look at this, so this is just the same as the definition of covariance between gxi and gxj. Okay, because here the xi and xj, so they are independent. So remember, they are IID, right? So then gxi and gxj, so they are also independent. So then the covariance is 0. So that is what we learned in chapter 4. Okay, so in other words, all those interaction terms, so here is the same as a covariance, so which is 0. So then we have only this square term, which is the variance of gxi. Okay, so then we have n of those square terms, right? So then that is the n multiplied the variance of gx1. Okay, so as I mentioned, so because all those xi's are IID, so you can also write this as n multiply the variance of gx2, and then so on. So they are the same. Okay, so those are the two formulas to calculate the expectation of variance of sum of a function evaluated at for those IID random variables. Okay. So now let's move to the next part. So now we are going to use those results to calculate some the expectation and the variance of x bar and s square. Okay, so here the x1 to xn is a random sample from a population with mean mu and a variance sigma square. Okay, so here this population we do not have any distribution assumption. So this is just a general population. So with mean mu and a variance sigma square. So it is not necessarily to be normal, right? This is just a general population. Okay, so then we have those three properties about the mean, the sample mean and the sample variance. So that is x bar and s square. Okay, so first one, the expectation of the sample mean is the population mean. Okay, the expectation of sample mean is population mean. Okay, so the second is the variance of the sample mean is sigma square divided by n. So here sigma square is the population variance. Okay, and n is the sample size, so number of observations in this random sample. Okay, and the expectation of s square is the population mean sigma square. Okay, so before we go through those the formal calculation, okay, so let's look at the meaning of this. The meaning, what is the meaning of those formulas? Okay, so basically now we are talking about the the sample mean and the sample variance to make inference about the population mean and population variance. Okay, so the first property tells us the expectation of this sample mean is the same as the population mean. And then the expectation of this sample variance is the same as the population variance. Okay, so that is actually a good thing, right? So that is because in chapter 2 I explained. So the expectation means, so on average, what is the value of this quantity? What is the expectation of the x bar? So on average, so if we draw this random sample multiple times, okay, and then each time we calculate a sample mean, so like x bar 1, okay, as we draw this, say m, we do this sampling m times, so we will calculate a number of sample means, right? Okay, and then on average, the average of those sample means should be close to mu, to the population mean mu, right? So this is a good thing, yeah, because we know, okay, the average of those sample means should be the same as the population mean. Okay, so in chapter 6, so this property is called unbiasedness. Okay, unbiasedness. This is beyond this semester, so you will learn this in the next semester. Unbiasedness. Okay, so if the expectation of some statistic is the same as the population parameter, okay, so then we will say this statistic is an unbiased estimator of the population parameter. Okay, let me write this. So if the expectation of this x bar, so I will just use this example. So this is the same as the population mean. Okay, so then x bar is an unbiased, so unbiased estimator of mu, of the population mean mu. Okay, so you will learn this in chapter 6. Okay, and then these formulas, okay, so here the type tells us, okay, the sample mean is an unbiased estimator of the population mean mu. Okay, and also the sample variance S squared is also an unbiased estimator of the population variance sigma squared. Okay, so the expectation of this is the same as the population variance sigma squared. Okay, so now let's look at how can we prove this. So in other words, how to calculate this. Okay, so the first one, the expectation of x bar. Expectation of x bar. So the definition of sample mean is this, the sample average, expectation of this sample average, right? Here, by the property of the expectation, so we can take the constant 1 over n out of the expectation. So then we have this, okay? And then this is the expectation of a sum of IID random sample, right? So then by the result, we just discussed this one. The expectation of sum of this will be n multiply the expectation of x1. Okay, so then this is just the expectation of x1. Or you can write this as expectation of x2, x3. Okay, so xi, either of the expectation of any of xi's. Okay, so which is the population mean, mu, right? That is the definition of this expectation, right? Expectation of xi is mu. Okay, so then we have shown the first formula. Okay, and then the second one is what is the variance of x bar, the sample mean? Okay, so the variance of sample mean, so that is defined in this way. Okay, And then by the property of variance, so we can take out the constant 1 over n out of the variance, but we need to square this constant. So we have 1 over n squared multiply the variance of the sum of xi. Okay, so again, we use the result we just discussed. So the variance of this sum. The variance of this sum is n multiplies the variance of each individual one. Okay, so then that is n multiply the variance of x1. Okay, so the variance of each xi, so that is the population variance, so which is this sigma square. Okay, so then we have this as sigma square divided by n. Okay, sigma square divided by n. Okay, so this one is, we also need to know this. So the variance of x bar. The variance of x bar will be the variance of the population divided by n. Okay, divided by the sample size n. Okay, so that is the second formula here. Okay, so the third one, to show the third one. Okay, so now we are going to use this formula. So the expectation of s squared. So now we plug in this, we call this the alternative formula for s squared. This alternative formula, so we discussed here. Okay, so for s squared. Okay, so this is the sum of xi squared minus n x bar squared. Okay, so which is this. Okay. So now let's try to evaluate this expectation. Okay, so here, by the property of expectation, so we can take this expectation psi into this brackets. Okay, so we have n minus 1 here. Okay, so the expectation of the sum of, so now we are going to use the theorem we just discussed. Okay, so the expectation of the sum of xi squared, so that will be n multiply the expectation of x1 squared. Right, so we use the result of this lemma here. Expectation of sum of a function will be n multiply the expectation of that individual function. So that is the n multiply the expectation of x1 squared. Okay, and then this one will be n multiply the expectation of x bar squared. Okay, n multiply the expectation of x bar squared. Okay, and now we can use the result we just shown this. Okay, so the expectation of x1 squared, so that will be the variance of x1 squared plus the square of ex1, right? So then we have the sigma squared plus mu squared. Okay, and then the n multiply the expectation of x bar squared. Okay, this one. So the expectation of x bar squared, so that will equals the variance of x bar plus the square of e x bar, right? So that is by the definition of the variance, right? The formula to calculate the variance. Okay, and then the variance of x bar, so we just shown, so that is the sigma squared divided by n, right? Plus, so the expectation of x bar, so which is mu, right? The population mean. So which is this is mu square, right? So then we have this. Okay, and then after some simple calculation, so we will see this is exactly sigma square. Okay, this is exactly sigma square. Okay, so again, this basically says the expectation of sample mean is the population mean mu, and the expectation of the sample variance is population variance sigma. So in other words, the terms you will learn in the next semester. So x bar and s square are unbiased estimator for mu and sigma square. Okay, so now let's think about the one thing about the sample variance here. Okay, so that is why we have here the n minus 1 in the denominator. So not n. So here we have the n minus 1 in the denominator. Okay, so based on these calculations, we will see. So once we have n minus 1 as the denominator for this sample variance, so then this sample variance will be an unbiased estimator for sigma square. Okay, so but if we have 1 over n, so instead of n minus 1, we have n in the denominator. So then the expectation, you can do the calculation by yourself. So the expectation of this quantity, okay, so I will write, let me write this as s prime square. So if we define this as this, okay, so we change the n minus 1 to n. Okay, so you will see the expectation of this. So it is actually up to a constant. Okay, this is not sigma square, the expectation of this. Okay, up to this constant n divided by n minus 1. Okay, the expectation of this is not sigma square. Okay, so in other words, here the s with this n minus 1 in the denominator. So this one is the unbiased estimator of sigma square. Okay, because this expectation is a sigma square, the population variance. Okay, and then here is one more note here. Okay, so the first one, the expectation of x bar is the population mean. So this is true even if so xi's are not independent. Okay, but they need to be identically distributed. So meaning they are from the same population with mean mu. Okay, they still need to be from the same population with mean mu. Okay. Okay, so let's take a 2 minutes break. Okay, and we will be back. So just want to check everything is okay so far.
Yes.
Okay.
Yeah.
Okay. Let's just give me 2 minutes. Okay, and I will be back. Okay. Okay, everyone. Okay, so you guys follows what we learned so far. Everything is okay.
Yep.
Okay. So now let's continue with the next part. Okay, so here we have some one more result about the based on the MGF moment generating function for the sample mean, okay, of IID random sample. Okay, so here we have this. So here x1 to xn is a random sample from a population with MGF mx. Okay, so here because x1 to xn, so they are IID. So then basically the MGF for all of them, x1 to xn, so they are all the same. So which is as the same as the population MGF. So that is mx. Okay, so then what is the MGF for the sample average? Okay, so this is the moment generating function of x bar. Okay, x bar is the sample mean of x1 to xn. Okay, so it has this relationship. Okay, so here the in this formula, so the t is like take the average, right? So divided by n. Okay, and then we take this mx evaluate for t divided by n to the power of n. Okay, so to see this, so this is just based on the definition of MGF. Okay, so the definition of MGF is the expectation of this. So now this random variable is x bar, so that is exponential of t x bar. Okay, so now we plug in the values. So t multiply sum of x1 to xn divided by n. Okay, so here the let's see this. Okay, so next we just write this. So the sum of this. Okay, so here we let y somehow miss one step here. Okay, so here we write y as the sum of xi. Okay, sum of xi. Okay, so then this will be the MGF of this. Here y is the sum of xi. Okay, so this means the MGF of the sum of xi evaluated at t divided by n, right? So this is also based on the definition of MGF, moment generating function. Okay, and then remember that we also have a formula for this sum of independent random variables for the MGF, right? So remember the sum, MGF of sum of independent random variable will be the product of individual MGF. So meaning multiplication, right? So then this will be the, I will write, this is the sum of this, right? So that is x1 to t divided by n multiply the MGF of x2 evaluated at t divided by n. Okay, and then so on up to xn, right? And then as I mentioned, so now x1, x2 up to xn, so they are IID. So all their MGF is the same, right? So which is exactly we will write the same as the population MGF, mx. So evaluate at t divided by n, okay, to the power of n. Okay, so as I mentioned, as we learned in chapter 4, so this technique is useful, to find out the sum of independent random variables. Okay, so once we look at the form of MGF, so then we can say what is the distribution of the sum of xi. So here, it is still useful to calculate to look at the distribution of x bar, right, by using this. So now let's look at two examples for this. So here, this one, the x1, xn, is a random sample from this normal population, so with mean mu, variance sigma square. Okay, so then let's look at the distribution and MGF of x bar. Okay, so based on this theorem, so the MGF of x bar is this. Okay, and then if we just expand this MGF and plug in the form of normal MGF, so we will have this. Okay, and then after some rearrangement, so we got this. Okay, so now can you recognize what is the MGF of this one? So which distribution have this MGF? Okay, so actually we calculate this in chapter 3 for the normal MGF, and this is also given in the table of our textbook. Okay, so this is also a MGF of a normal distribution. Okay, so mean is still mu. Okay, but the variance is sigma square divided by n. Okay, so here we can see x bar based on the form of its MGF. So the x bar follows this normal distribution. Okay, so this one, we need to pay attention. So the mean is still mu. Okay, but the variance now is sigma square divided by n. Okay. So this is also a special case of the previous result we have shown here. So the variance of x bar is sigma square divided by n. Okay. So the variance is sigma square divided by n. Yeah. So I want to mention this because I saw some students, they forgot this n. Okay. We need to, for x bar, we need to divide by n, its variance. Okay, so then this is the distribution of x bar from the normal population. Okay, let's see another example. So now here the random sample is from a gamma distribution. Gamma distribution here. Okay, so again, to calculate the MGF of x bar, so we can use this formula. Okay, and then we can also here I will directly give you the result and let you guys to try the detailed calculation. Okay, so after we plug in the values, so we will see the MGF of x bar is this. Okay, so this is also a gamma distribution, the MGF of a gamma distribution. Okay, so which is this one? So the first scale parameter becomes n alpha. Okay, and then the beta parameter, the shape parameter, so now is beta divided by n. Okay, so then we can say this x bar also follows a gamma distribution. Okay, the scale parameter is n alpha. Sorry, the shape parameter is n alpha, and the scale parameter beta now becomes beta divided by n. Okay, so this is the MGF of the x bar. Okay, the sample mean. Okay, so next one. So in some cases, so this MGF technique will not work. Okay, so now let's introduce another tool. Okay, so which is called the convolution formula. So this convolution formula. Okay, convolution formula. So basically, this convolution formula is also a method to find the distribution of sum of independent variables. Okay, so here we will use the example of bivariate random variable, two variables, it's the sum of two random variables. Okay, so here this theorem is this. Okay, so here x and y are independent continuous random variables, So each with PDFs fx and fy. Okay, so then the PDF of z equals x plus y. So there is a formula. So we call this convolution formula. Okay, convolution formula. So this formula this gives us a quick formula to calculate the PDF of z. So which is this. Okay, so this is equals the fx. So evaluate at w, multiplied fy, evaluate at z minus w, and we need to integrate out the variable w. Okay, so how can we get this formula? So now let's look at the proof here. Okay, so this formula is just a application of the transformation technique or the Jacobian method. So we learned. So now we just simplify this Jacobian method to a single formula. So which is called convolution formula. Okay, and the name of this sum. So in statistics, there is a special name for the distribution of a sum of two random variables. So that is called the convolution. So here Z is called the convolution of x, y. Okay, Z is the convolution of x, y. Okay, so to prove this, so we will just make the transformation as Z. Z is x plus y. Okay, and W, so we let W to be any one of the random variables. So here we let W equals x. Okay, so then it is easy to calculate the Jacobian. Okay, so Jacobian is just 1 here. Okay, so using the previous Jacobian formula for this method, so we can obtain the joint PDF of ZW. Okay, the joint PDF of ZW is this. So now we plug in here the x is W. X equals W. Okay. And then y. What is y? So y is Z minus W. Right? So we just plug in the solutions for x and y. Okay. And multiply the absolute value of Jacobian, so which is 1. Okay. And then now this becomes this. Right. So here, this is because x, y are independent. X and y are independent. Okay. So then their joint PDF can be factorized as a product of each individual PDF. Fx multiplied xy. Okay, so then we can just integrate out W. Integrate out W. So then we will obtain the marginal PDF of Z. Okay, so you guys follows this idea, right? Okay, so this is just the application of the Jacobian technique. So now we just put this result as a single formula, so which is called the convolution formula. Okay, so now let's just quickly look at one example. Okay, because we have multiple methods to calculate this. Okay, so here we have x and y are independent random variables from this uniform distribution. So now let's find the PDF of z equals x plus y. The sum, z is the sum of x, y. Okay, so let's think. First, let's do this as a kind of review. So, how many methods we have learned for this? Okay, to find this transformation, or specifically the sum of two random variables. How to find that PDF? Okay, I think at least 3 or 4 methods we have learned, right? So the first one is the general method based on the. I will not go over details, so I will leave for you guys to read. So first one is based on the general method on the probability, or we say the method based on the CDF, right? So this is a general method. Okay. The second one, so that is based on the MGF. Okay. So remember we have the, the formula to calculate the MGF of a sum of random variables, sum of independent random variables. So that is the MGF method. Okay. And the third one, so now we call it the convolution method. Okay, so which is just a special case of the Jacobian method. Okay, so you can either use the Jacobian method to do this, or directly use this convolution formula. So basically, they are you can think them as two methods or just the same method. Okay. Okay, so now let's just look at the third one, the convolution formula. Okay, so the convolution formula says, so this PDF of z, sum of x, y, so that equals the integral of the products of those two marginal PDFs of x and y. Okay, we need to integrate out w. Okay, and then here the x, y, so they are just the uniform distribution. Okay, so which is just here I use the indicator function, right? So this is just 1. Okay, 1. Okay, and the support of this is from 0 to 1. This support of this one is also from 0 to 1. Okay. So here, the only thing we need to consider is the range of this integration. The range of this integration. Okay. So here, if the z is from 0 to 1, so the range of this integration is from 0 to z. Okay. And then the range of z is from 1 to 2. So the range of this integration is from z minus 1 to 1. Okay, I will leave you guys to figure out the more details here. Okay, so then we will have the two different forms of this PDF of z. So based on the range of z. Okay. Okay, so then this is the convolution formula to calculate the sum of two independent continuous random variables. Okay, so the last part, we have two results. So that is about the distribution of the sample mean for the location scale family and the exponential family. Okay, so as I mentioned, the exponential family, so that is optional for our course. But I hope you still have some impression about the concept of this exponential family. Yeah, because you will learn more details in the next semester. Okay, in the statistical inference stat theory 2 course. Okay, so in that course, the exponential family will be widely discussed. Okay, so here, due to the time so I will skip this part for exponential family. Okay, so basically these results are saying, so for exponential family distribution, so we have a some form of formula to describe the distribution of the sample mean, okay, of the sample mean of the exponential distribution. Okay, so what I want to briefly mention is the distribution of the sample mean for the location scale family. Okay, so this is also easy to understand. Okay, so remember for the location scale family, so the basic idea is we call this standard distribution, Z. Okay, and then for example the standard normal distribution. Okay, like this. Okay, so then we can generate a family of random variables or a family of distributions defined as X. So X is has this relationship with Z. So that is mu plus sigma Z. Okay, so here the mu is called the location parameter, and the sigma is called the scale parameter. Okay, so for example, this is the normal distribution with mean mu and the variance sigma square. Okay, so in this way, the PDF of X will be like we are changing or shifting the position of Z. Okay, so mu basically is a location parameter. Basically, we shift the standard normal distribution to the position of mu. So that is a location parameter. And the sigma is the spread parameter, or we say the scale parameter, determines the spread of this family of the PDFs of this distribution. Okay, so this is the location scale family we call. Okay, so now we consider this. So we consider random sample x1 to xn. Okay, x1 to xn, and z1 to zn. Okay, so here the x1 to xn, so that is from this x1 to xn, so that is a random sample from this distribution, so indexed by x. Okay, and then we also have z1 to zn. Okay, so z1 to zn is drawn from the standard distribution of z indexed by z. Okay, so then we will have this relationship. So it's easy to see. So x bar is also equals mu plus sigma z bar. So their sample means also has this relationship. Okay, so now what is the relationship between the PDFs of z bar and x bar? Okay, so this is also the same as the population PDFs. Okay, so that is this G, say if G z bar, so this is the PDF of z bar. Okay, this is z bar. Okay, so then the x bar will have this PDF. Okay, so which is this one. Okay, so this is basically the same as this relationship between x and z, the population PDF, the PDFs of the two population. Okay, so like here inside this PDF, so we standardize this x by subtract mu divided by sigma square, and then we scale this by sigma. Okay, so then this relationship also hold for the PDFs between x bar and z bar. So they also have the same relationship like this. Okay, so this is the meaning of the result here. Okay, about the distribution of sample means in this location scale family. Okay, so then that is all for this part. Okay, so basically that's about the properties of the sample mean and sample variance. Okay, so any questions so far? Okay, no question. Okay, so we still have about 25 minutes. So now let's move to the next part. Okay, let's move to the next part. Okay, so okay, so we just talk about the properties. Okay, some results and formulas for the sample mean and the sample variance. Okay, so next part we will be more specific. Okay, more specific. So here we are talking about the sampling from the normal distribution. So in other words, we are talking about the X bar and the I square, sample mean and variance from this normal distribution. Okay, normal distribution with mean mu and the sigma square. Okay, so actually before we go over the the results in this part, so I want to say actually many of them, so you guys already seen probably somewhere in your introductory statistics course. Okay, so basically we are talking about the distribution of X bar, S square. Okay, and also some related statistics built on X bar and S square. Okay, so and here they are all from the normal distribution. Okay, so what I'm going to do is like this. So we will first go over those results. Okay, I will explain some of them. Okay, and then next we will comes to the proof. Okay, so the proof of those results and how to calculate them. Okay, so basically we have I would say about four results. So regarding the distribution of X bar and S square from the normal distribution. Okay, so first one, let's start with the first one. Okay, so here, as I mentioned, x1 to xn, so now is a random sample from the normal distribution. Okay, so and the X bar is the sample mean and the S square is the sample variance. Okay, so then we have the following results. Okay, first one, so X bar and S square, so they are independent. Okay, second, do you know this? Do you know this before? So what is the distribution of X bar? Okay, so here the X bar is also has a normal distribution with mean mu, and the variance is sigma square divided by n. Okay, so and this part we already proved. Okay, so in the previous one, so using which method? So based on the MGF, right? Based on the MGF. Okay, so we already shown this. Okay, so this tells us X bar also has a normal distribution with mean mu. Variance is sigma square divided by n. Okay. Okay, and then the third one. The third one is about the distribution of S square. Okay, so this quantity. So we need to somehow make some standardization. So I would say this S square multiply n minus 1. So remember the n minus 1 is in the denominator of sample variance, right? So we need to multiply this and then divide it by the sigma square. So sigma square is the population variance. Okay, so this quantity has a chi-squared distribution with n minus 1 degrees of freedom. Okay, so basically those are the three properties of X bar and S square from the normal distribution. So first, they are independent. X bar has a normal distribution and S square has a chi-squared distribution. Okay, so this is, just briefly to remember this. Okay. Okay, so next, I think normal distribution, so we are all familiar with this. So now let's spend some time talking about the chi-squared distribution. chi-squared distribution. Okay, so here the definition of a chi-squared distribution. So the PDF of a chi-squared random variable. So we have seen this before in chapter 3. So I briefly mentioned that. So that is a special case of the gamma distribution. So where the alpha parameter is p divided by 2, and the beta parameter is fixed at 2. Okay, so then we will just replace the alpha parameter, the shape parameter, as p divided by 2. Okay, so which is here. Okay, this is the PDF of the chi-squared distribution. Okay, and I have attached a plot of the PDF of the chi-squared distribution. Okay, so then for the chi-squared distribution, there is only a single parameter, right? So which is p. Okay, so here the p is called the degrees of freedom. Degrees of freedom of the chi-squared distribution, p. Okay, or similarly we call the df, degrees of freedom of the chi-squared distribution. Okay, so here are some curves of the chi-squared PDF for different dfs, for different degrees of freedoms. Okay, so like this. Okay, so we can see the chi-squared distribution is positive. The support is non-negative. Okay, non-negative. Okay, and it is also right skewed. So long tail is on the right. It is positively skewed. Okay, so this is the shape of the chi-squared distribution. Okay, so the chi-squared distribution is let's look at some property of this chi-squared distribution. So given in this lemma. Okay, so we will use the chi-squared p to denote a chi-squared random variable with p degrees of freedom. Okay, or sometimes to make it more clear, we can write the p in brackets like this. Okay, this is a chi-squared distribution with p degrees of freedom. Okay, so those are some facts about the chi-squared distribution. So first, so if the z, random variable z, is from the standard normal distribution, okay, so then the square of z follows the chi-square 1 distribution. So means chi-square distribution with 1 degrees of freedom. Okay, so that is how the name chi-squared comes into play. Okay, that is the square of a standard normal distribution is a chi-squared distribution. Okay, okay, and here we should know this. Okay, we actually already shown this in chapter 2. So when we talk about the variable transformation, so remember we have the y equals x squared. Okay, so and the x follows the standard normal. And then in the previous example, so we have shown this follows a chi-square distribution. Follows a chi-square distribution. Okay, so next fact, that is about the sum of independent chi-squared distributions. Okay, so here if x1 to xn, so they are independent chi-square distributions, and xi follows the chi-square pi. So pi is the degree of freedom for each xi. Okay, so they are independent, and they also follows the chi-square distribution. So the sum of them also follows a chi-squared distribution with the degrees of freedom equals to the sum of each individual degrees of freedom. Okay, basically sum of independent chi-squared random variable also has a chi-squared distribution. Okay, and then this one we also shown before. Okay, like in chapter 4. Okay, so in chapter 4, the previous example is basically we use this MGF technique moment generating function to find out the sum of gamma distribution. Okay, sum of gamma distribution. Okay, so here the chi-squared distribution is a special case of the gamma distribution. Okay, previously we showed if xi follows gamma, alpha I beta. So by using the MGF method, so we can show this sum of xi follows this gamma distribution. So now we sum up the alpha parameter, the scale parameter, and the shape parameter. I'm sorry, we sum up the shape parameter. So alpha is the shape parameter, and beta is the scale parameter. So beta parameter is the same, and this alpha parameter will be the sum of each individual ones. Okay, so here the chi-square distribution is a special case of this gamma distribution. Okay, so then we will see this is proved. So the degrees of freedom will be the sum of this. Okay, so those are the results of the chi-squared distribution. Okay, so the next one. Okay, so some notes here. So the first one, so by combining part A and part B, okay, so we have this result. Okay, so here the x1 to xn is a random sample from the standard normal distribution. Okay, so then by part A of the previous of the lemma, okay, so what is the distribution of xi square? Okay, so that is the chi-square 1 distribution, right? And then what is this one? So the sum of squares, okay, sum of x1 square to xn square. Okay, so by part B of the lemma, so this also has a chi-square distribution, so with degrees of freedom n. Okay, so we have n, the sum of n ones, right? So that is n. Okay, so the second one. So now we have x1 to xn. So that is a random sample from this normal population, normal distribution. So with mean mu and the variance as sigma square, variance of sigma square. Okay, so then this standardized version. So basically this is the same as the above one, right? This is the same. Okay, the sum of those standardized normal random variable also has a chi-square distribution with degrees of freedom n. Okay, so basically the intuition about chi-square, so that is related to the square of normal distribution. Okay, so then those results are also related to the square of normal random variable. Okay, so far we haven't proved this, but we will see the proof of this theorem later. Okay, so here this sample variance s square also kind of related to chi-square distribution. Yeah, so if you remember the formula of s square, so it also contains the square of xi, right? So that is why this follows a chi-square distribution. Okay, we will see the proof soon. So after I finish explaining all those results. Okay, so those are all the results about the chi-squared distribution. Okay, so now let's look at the one lemma. That is the result about the linear sum. So linear sum of normal random variables. Okay, so that is about normal random variables. Okay, so this one is kind of generalized results we learned in chapter 4 about the multivariate normal distribution. Okay, so here we have xi. Xi follows a normal distribution. So with different mu and variance, so mu j and sigma j square. Okay, and they are independent. Okay, and now we have a set of constants aij and brj. We have these constants. So now we defined those two random variables u and v. So they are linear sums of xj of those normal random variables. Okay, so then we have the following two results. The following two results for those linear sums of normal random variable. Okay, so here the ui and the vr are independent if and only if their covariance is 0. Okay, and further, we can calculate their covariance. So their covariance will be this. Okay, so basically this is a interaction term with A and B and contains the variance of sigma j. Okay, so second part is, so those two vectors, u and v. Okay, so remember u and v, so they are linear sums for of those normal random variable. So they are independent if and only if, so ui is independent of vr for all pairs of I and R. Okay, so this is the way, the textbook to express those results. Okay, so let me, a little bit complicated here. Let me explain in more plain words about those results. Okay, so basically the part 1 of this lemma basically implies this. Okay, so that is for two normal random variables to be independent. Okay, so we only need to show their covariance is 0. Okay, so remember in chapter 4, so we talk about this. So the covariance of two random variable. Okay, so if this is 0, this, in general, this is not necessarily implies x and y are independent, right? So in chapter 4, we said this. So x and y, if they are independent, so then their covariance is 0. But the reverse, this way, is not generally true. Okay, in most cases, it is not true. Okay, but there is an exception. So that is for the normal random variables. Okay, so for normal, this is true. So that is covariance is 0. Is the same as to say, so they are independent. Okay, this is only for normal random variable. Okay, so that is for part A. Okay, the meaning of part A here. Okay, and then what is the meaning of part B? Okay, so for part B is about this. That is about the concept of pairwise independent and the mutually independent. Okay, so still as we mentioned in chapter 4. So this mutually independent is an important concept for multiple random variables. Okay, so mutually independent, by definition, so that is the joint PDF, right? So the joint PDF xn can be factorized as the product of individual one, right? Okay, so this mutually independent also implies pairwise independent. Pairwise independent means any two of them, a pair of them, x1 to xn, are independent. Okay, so mutually independent implies pairwise independent. Okay, and we also said the reverse is not generally true. So the pairwise independent does not imply mutually independent. Okay, but there is also an exception. So that is for the normal. For normal, this is correct. For normal, this is correct. Okay, so if this, for more than 2 normal random variables, okay, so pairwise independence also implies mutually independence. So this is only for normal random variable. Okay, so that's the meaning of these results. Okay, for the rigorous proof, I will ask you guys to look at the textbook. Okay, a more rigorous proof. Okay, so then that is about the chi-squared distribution. So we discussed, and also the 2 results for the normal distribution. Okay, so now let's turn to the next page. Okay, so remember the topic of this part is the random sample from the normal distribution. Okay, so we have mentioned the X bar follows the normal distribution with mean mu and variance sigma squared divided by n, and the S squared sample variance follows the chi-squared distribution. Okay, so the next result is this. Okay, so that is, we are talking about this quantity. This one is related to both X bar and S squared. Okay, the sample mean and the sample variance. Okay, so here the X1 and Xn also a random sample from the normal distribution. Okay, so we want to know this quantity. So that is X bar minus mu divided by S divided by square root of n. Okay, so actually this quantity follows a T distribution, student T distribution. Okay, so we will show this. Here I just did some algebra, to simplify some notations for the proof of this. Okay, but now let's first look at this definition of student T distribution. Okay, I guess you must have learned this in your introductory course, right? Okay, so here the X1, Xn is a random sample from this normal population. Okay, so then this quantity, this should be X bar. So X bar minus mu divided by S divided by square root of n. So this quantity has a student T distribution with n minus 1 degrees of freedom. Okay, so and what is the PDF of the T distribution? So then if a random variable T follows a student T distribution, so here the P is also the degrees of freedom, the only parameter of this student T distribution. Okay, so the PDF of the T distribution is given in this form. Okay, so I also have that plot for the T distribution with different degrees of freedom. New here, different degrees of freedom. Okay, so here we can see the T distribution. It is also symmetric around 0. Okay, and then with the increment of the degrees of freedom, okay, so then the peak is growing higher and higher. Okay, for those PDFs of the T distribution. Okay, and when the degrees of freedom is close to infinity, okay, so then this is the same as the standard normal distribution. Okay, so when the degrees of freedom of T distribution goes to infinity, so then this T distribution becomes the standard normal distribution. Okay. Okay, so this is the property of the T distribution. Okay, so now let's look at some other properties. Okay, so here if the degrees of freedom P is 1 for the T distribution, So then this t distribution becomes the Cauchy, this Cauchy distribution. Okay, so remember what is the interesting property of this Cauchy distribution. So this expectation does not exist, right? The expectation of Cauchy distribution does not exist. Okay. Okay, so in other words, when p is 1, the mean of the t distribution does not exist. Okay, so that this is another interesting property of this student t distribution. Okay, so here in random sample setting, okay, so in other words, so remember that this definition is saying, okay, so we have an n random samples. So then this quantity follows the t distribution with n minus 1 degrees of freedom. Okay, and in other words, if this random sample contains only 2 observations, that is n equals 2. So then the degrees of freedom p of the t distribution is 1. Okay, so then the sample mean, not sample mean, the mean, the population mean of the t distribution does not exist. Okay, and the second note is about the moments of the t distribution. Okay, so only the p minus 1 moments exist for the t distribution. Okay, so in particular, so if p is greater than 1, okay, so we mentioned if p is 1, so then the expectation does not exist. If p is greater than 1, then the expectation of the t distribution is 0. Okay, so that is why the t distribution is also symmetric and has a peak at 0. Okay, so if the degrees of freedom is greater than 1, so the population mean, the mean of the t distribution is 0. Okay, and the variance, so we can calculate the variance given the PDF, right? So we can see the variance is given by this number. So it's p divided by p minus 2. Okay, so this exists for p greater than 2. Okay, so next note, so the MGF of the t distribution does not exist. Okay, MGF does not exist. Okay, so and the next one, the t distribution, so that is usually given as this quotient, right? This ratio, the quotient of a normal distribution, of a normal random variable versus a chi-squared random variable. So like this ratio. So the normal random variable is in the numerator of this ratio. Okay, and this chi-squared random variable is in the denominator in this ratio. Okay, so that is like this form, the normal mean and the normal sample variance. So like this forms this ratio, this quotient. Okay, so this form of variable, the ratio of a normal and the chi-squared random variable follows this t distribution. Okay, so we will prove this probably in the next class. Okay, okay, so let me finish the last result. Okay, the last result here. Okay, so we have the last result about that is about the ratio, distribution of a ratio of 2 independent normal sample variance. Okay, so here the x1 to xn is from a normal distribution with mean mu x and a variance sigma x squared. Okay, and we have another group of random variable, or y1 here I will write ym. Okay, so here there will be m observations in the second random sample. So y1 to ym, m. Okay, so that is from another normal distribution. So with mean mu y and variance sigma y square. Okay, so now we want to find the ratio of this, the ratio of sx squared versus sy squared. Okay, so here they are the two sample variance of x and y. Okay, so actually this quantity follows what we call the F distribution. F distribution. Okay, so the letter F is named in honor for Ronald Fisher, so a famous statistician. But the person did some theoretical work for the F distribution is this one. Okay. Okay, so that is again as we mentioned above. So x1 to xn is a random sample from a normal distribution, and y1 to ym is a random sample from a another normal population. Okay, so then the ratio containing the two sample variances, okay, has a F distribution. Okay, so here the F distribution has 2 degrees of freedom. Okay, so first degrees of freedom is for the numerator, so which is n minus 1. Okay, so that is the number of observations in the numerator. So that is n here, which is n minus 1. Okay, and the denominator degrees of freedom is m minus 1. Okay, and what is the form of the F distribution? So it's like this way. So basically it has 2 parameters, P and Q, corresponding to the numerator and the denominator degrees of freedom, respectively, P and Q. Okay, so basically the F distribution, this F distribution is derived from the ratio of 2 chi-squared distribution. Okay, so here the U and the V, so they are from the chi-squared distribution, and they are independent. Okay, they are independent. Okay, so then the U and the V, the ratio contains U and V, divided by the degrees of freedom, so it has an F distribution. So it looks like this way. Okay. Okay, so the F distribution, so in your introductory course, so that is used for the analysis of variances. Okay, ANOVA method. Okay, and then here there are some interesting property of the F distribution. Okay, so if X follows F distribution with degree of freedoms P and Q, so then 1 over X follows F distribution, switching the 2 degrees of freedom. Okay, so the last property is if X follows the T distribution with degrees of the freedom Q, so the square of X follows the F distribution. So the numerator degrees of freedom is 1, denominator degrees of freedom is Q. Okay, so basically those are the properties of a normal random variable. Okay, so basically we are talking about four distributions related to the mean and variance, sample mean and variance. Okay, briefly, you know how you can remember those. Okay, so basically X bar sample mean follows a normal distribution. So sample variance S squared follows a chi-square distribution. Okay, and the ratio of X bar and the sample variance follows a T distribution. Okay, and the ratio of 2 sample variances follows a F distribution. Okay, so this is a summary of all the results in this part. And we are going to we have to stop here. Okay, and next class, so we'll basically show the proof of those results. Okay, and also finish the last topic, so which is the order statistic. Okay, so this is the end of the class. Okay, thank you everyone. So
Thank you.
Okay,
Thank you.
Okay, see you Monday for the next class. Okay,
All right.
okay, bye bye.